Okay, so let's look at one more thing. Again, we're going to talk about velocity here. And again, if I've got a position versus time graph, and you'll see a lot of these graphs, so get used to these, okay? Here's my position, okay? And I'm going to use P instead of X, so we're clear on some of these things. And the position would be X, delta X over delta T, okay? Position, or you could say X, it's the same. Right now I'm using the same interchangeably. The idea is this. Now, let's say, rather than, when we did this last time, we said, well, hey, we're going to start at 0, and we're going to end out here somewhere. And there was some sort of straight line that got us from the beginning, from an initial standpoint, from our initial to our final, okay? There was some straight line. But let's assume for an instant that wasn't the case, because oftentimes, when you start from a dead stop, you don't go the immediate speed you're going to go. What you're going to end up doing is you're probably going to do one of these. You're going to slowly start to take off, and then you're going to go a little faster, then you're going to go slower, you're going to kind of do one of these things, right? You might go back and forth, but ultimately, you have what we call an average velocity, and this is different than vector. Vector is with an arrow, and average is marked with just a line over V. I know this gets a little confusing. I know you guys are like, Mr. A, why are you drawing them so similar? I didn't come up with these, but this is how we mark them. But an average, this is an average velocity, okay? And what that means is an average velocity is pretty much the same thing we just talked about. It's pretty much our delta x over delta t, all right? Where we look at our position, our time final versus our time initial, and our position final, okay, versus our position initial, right? So this is, again, we did this before, x final minus x initial over our time final minus time initial. The problem with this, the good and the bad, is that what we're doing is we're not catching all of this up and down motion, right? Because again, if it's a constant velocity, if we go back to our original position here, right, we said that at any point in time, if it's a constant, and this is important, this is a constant, right? Our position change over time change is constant. It means that this slope right here is the same no matter where we are on the curve, right? That change, that big X, that big triangle is the same essential shape as this triangle, right? It's the same shape, it's the same angle, and this is the same ratio, right? The ratio of let's say this is our delta X and this is our delta T, right? This is delta X, and I'm going to call it prime for a minute, and this is our delta T prime. That ratio, right, 10 over 2 is the same as 5 over 1, right, which is the same as 20 over 4. So no matter where we go, that ratio is always the same. And that's a constant in this case because it's position versus time, and this slope represents a constant velocity. And I lose some people here, but I want to make sure you really clearly understand this. It's constant means that the slope is constant. Our speed never changes, okay? And that means that I'm going at a constant 60 miles an hour. Now you're saying, well, but that's an angled line. Well, that's because it's position versus time, not velocity versus time, not our speed versus time. This is our position. This is Dallas. This is Fort Worth. This is initial. Our time initial, when we start the watch, this is 45 minutes later. So if you can kind of think of it as rotating it to the side, and we're really saying Dallas, big D, and big Fort Worth, right? And it's that distance over a time. However, on this scenario, right, we're looking at that distance. This is still big D, right? And this is still Fort Worth. But you'll notice that I might go a little slower initially and go a little faster. Maybe I'm stopping off at the Quick Trip over here. Gonna go to the old QT, pick up some coffee, right? Then all of a sudden, I look like I'm running short, so I'm going to go faster and faster. I'm going to try and cover more distance, right? In a shorter amount of time, I've covered more of this distance, right? Here I've covered, in a let's say a similar amount of time, because let's say this time here is the same as this time here. I've covered a very short distance, whereas here I've covered a really long distance, a great bigger distance. And so my speed is different. Maybe I'm outrunning the cop over here. Here's the cop is coming after me, and he's got that light bar, right? We're like, woo, woo, right? We're sitting here going, they're coming after you, right? And, because this is, I think, Brylan over here trying to outrun the cops. But we're looking at our time and our speed, and you can see that we're covering bigger distance in shorter amount of time versus here where I'm stopping at the QT, right? And even if I stop at the QT, it might even look more like this, where I'm coming in and I'm going to stop. I mean, my distance doesn't change as time goes on. This is me going into parking. I'm parking, and then I'm going to go walk into the QT. I'm hanging out. My car hasn't moved at all. Then I get back into my car and I start going, but I realize I'm losing some time, so I'm going to go faster. And then maybe again, I'm over here. Now at this point, from here to here, again, my change in distance is nothing really, even though my time continues. This is like I'm stuck in traffic, right? It's a straight line. I'm not going anywhere. My distance doesn't change, but my time, carries on, because time always carries on. So what's different about this curve versus, again, this curve? This curve shows me, or assumes I'm having a constant speed. It doesn't show me any of this detail. Maybe this is the exact same thing as this, right? But I don't see the detail that I had in here. I don't see in this area where my QT stop is, where my traffic is, right? But I can get there. You could have gone, in a different route and gone this constant speed, but I had to go do this, or Brylan had to go do that. And so what we're looking at is that overall distance, change in distance over change in time. That is our overall slope, our overall average slope, and our average speed. It's delta x here, right, versus our delta t. Okay. Now, however, again, we look at the whole story. At any point in time, right? At any point in time, I'm going to be looking at right here. What's my speed at this? What's my speed right here? My speed right here is 0 meters a second. I'm not traveling at all. Right at that point, that's my speed. Same thing down here. But that doesn't get calculated in the average. That's called the instantaneous velocity. It's the velocity at any single point in time. So the velocity at any point in time t. Okay? Right here, what's my speed? My speed is really, really fast. Now, you're going, well, Mr. Ray, what is my speed? Well, the speed, guys, the speed at this point is the slope at that line. So it's at that point. So it's that slope right here. And we'll talk about how we get that in a second. But it's this distance over that time. That is our slope. That is the speed at that point in time. But you can notice over here, that slope is different. And that slope is what's called tangent. All right? So if I think about having a circle, right, and I have a line, okay, that's tangent, which means it touches the circle at one point, okay, and the angle between the radius of the circle and the line touching it is perpendicular. And that's what tangent means. So the tangent line at any point along the curve represents the slope at that point on the curve. So this again is our slope. Okay, delta x and delta t. And this again gives us our instantaneous velocity. So let's look about how we kind of get there. I'm gonna give you an example of how we get to the instantaneous velocity. All right. So again, let's look at another x versus t, or position versus position, or x versus time graph. Okay. And let's look at something that's fairly simple. Let's say we look at something like this. Okay. All right. So what's going to happen, I think what I'll do is I'll come over to here and I'm going to erase all of this because I need a new layer. Okay, I'm going to bring this guy down below here. So let's look at this. Now if I look at this, right, I can say, hey, you know what, here is my, let's look at my, let's try and figure out the instantaneous velocity at that point in time, t, at that point in time, t. And what is my, well, I mean, if I look at that, I have a position, right? But my velocity is the slope at that point in time. So let's look at this for a second. Let's see. So if I were to say point here and point here, I could say, well, here is a slope for a fairly wide region around that point. So here's, let's say this is okay. Here's my t final and my t initial, and here's my position initial and my position final. Okay, so my slope is from here to here. I'm gonna do this in green. Okay, my slope is from here to here. Now that may or may not be the slope at that line. Don't know, but I can kind of get a good estimate, right? So I can say, well, look, here is my delta x, which is equal to x final minus x initial. And here is my delta t, which is equal to my t final minus my t initial, right? And the slope, okay, which is my velocity, is equal to my delta x over my delta t, which is equal to my x final minus my x initial over my time final minus my time initial, okay? And so that's my one slope, but that's not actually at that point. That's not the instantaneous. It's, again, it's an average. It's an average speed, right? It's an average speed or average velocity from this time between these two times. Now, what if I took and I said, well, wait, you know what? I'm gonna take it a little bit smaller. I'm gonna take it a little bit closer around that point. So here's my new position, right? And my new position. And here is my new slope. From there to there, right? I'm getting closer, aren't I? So I can keep getting closer and closer and closer until I finally get to that point where I'm getting that tangent line, which is tangent to that surface at that point. And that's my instantaneous, that slope of that line, that slope is my instantaneous velocity. And so what am I doing? Well, I'm taking a delta x, okay, as my delta t, so the instantaneous velocity is delta x over delta t, okay, as delta t approaches 0. All right. So for your non-honors folks, you don't need to necessarily worry about this portion, and then what I'm about to say, you honors folks, you need to. This is an issue where we're talking about derivatives, right? This is starting to be the derivative, where I'm taking my delta x, and as my delta t approaches 0, I'm getting into derivatives. The derivative of x dx dt is my velocity. So you can start to see how calculus is starting to play into this, and we'll see how we can do this with acceleration as well, okay?